Okay, so ladies and gentlemen, today's session is very important. You will be learning how do you implement the LSTM that you have learned in my previous session. There will be two parts to today's session. The first session would be an exercise session, the hands-on session, wherein we will be trying to implement the concepts that we have learned using long short-term memory, LSTM, in my previous class. Followed it up with attention mechanism. Okay, so both of them are quite important. And today's exercise that you're going to learn today, tomorrow you are going to implement a similar one in your hands-on session. So kindly pay attention. Okay. So agenda for today's exercise is to predict a next word using LSTM. What is LSTM? Long short-term memory means? Why did we learn LSTM? Why did we start learning LSTM? What was the need to learn LSTM? To deal with larger data. What type of data? Sequential data. Okay. What was the problem with RNN? So, because of vanishing gradient descent, what was happening? What was happening due to vanishing gradient descent? It was not able to remember large amount of data. The memory was getting vanished. Yes or no? So RNN is still useful, but it will be good if you deal with a small amount of data where you don't have to remember long sequences. If you want to go a little bit more with the length of the sequences, then you will have to go for enhanced version of RNN only. It's a recurrent neural network enhancement only. What is it? LSTM, either LSTM or GRU. We are studying LSTM. Okay. But yes, of course, LSTM also has got its own drawback that we will see later. But as of now, we are on to its heavier advantage side that, okay, it's far more advantageous to use LSTM than RNN. So we are going to quickly use one example to see how are we going to predict next word in the sequence while using an LSTM. Okay. What was your previous exercise that I have taught you so far? Text pre-processing. है ना? So what were the basic steps involved? Tokenization, lower casing, lemmatization, stemming, stop words, removal, and word embeddings. The word embeddings was very crucial. Either you can initialize your word, the vectors that you're generating out of your word into random vectors, or you can go for pre-trained vectors. So all these steps are the basic heart and soul when you are dealing with any type of NLP applications. Because of course the data is going to be sequential in nature. So the text pre-processing steps remains the same. The change would be in the implementation of your sequential model. Either you will be taking up an RNN model or an LSTM model or a GRU model, or if you want to build any transformer model, whatever it is, any NLP application. Clear enough, guys? So quickly moving on for today's exercise, the first step would be obviously prerequisite part, import all the libraries that you're trying to work while using this particular application. So what am I importing here? But of course, by default, I'm using PyTorch. I'll, call that library. Apart from that, here I'm building a bigger sequential model wherein I am working with large amount of data. Every word, will be converted into some sort of vector. So humongous amount of computations will be needed. So in that case, you have to call all the libraries that are involved in doing all heavier mathematical calculations. So here I am calling which libraries for the same? I am calling here NumPy and pandas. Why pandas? So now we will be working with data frames. Okay. So for that reason I have to now call pandas also. So I am calling I'm importing pandas, I am importing NumPy, I am importing PyTorch. I have to build a model using PyTorch, for which I am calling basic neural network, library called as NN. And then I will have to build an optimized version of my model. So I am supposed to use optimization algorithm, for which I'll be calling optimization from the PyTorch, from Torch as Optim. Okay, optimization library. So all these things we have imported. That is your basic prerequisite. Follow up and memorize these steps. They are important. Okay, so once you have done, what do you require is, you require your data. Either you take a data set or you create your own data set. Here, since we are trying to build a simpler model, I am creating my own data set. If you want, you can either go for reading a text file. That also works in your applications. Okay. So here I am creating my data set. How do I create my data set? By first creating a dictionary. So the first step was you import your libraries. Second step is to create your data set by creating a dictionary here, wherein I am calling the key as text and I am giving its value as a list of movie review strings. Okay, so what is my data set here? The movie was fantastic and very engaging. I hated the acting and the storyline. It was boring and lacked depth. I mean, it's a mixed reviews that have been attached one after another, kept as a list and given as a data. So now what is the aim? The aim is, if suppose I am telling the movie was fantastic and very dash. So the model should be able to predict engaging for me. Are you clear enough? Yeah. So that is our task, and that is this data set that we have created for it. Now, first and important part, once you have prepared your data set, you try to create a data frame from your data set to work on. So here comes usage of what? Pandas. You are all proficient with pandas, I suppose. Okay, so I am not going much in depth there. I am creating a data frame from my data set. Once I am done that, now my text pre-processing start. What is the first step towards it, guys? Input tokenization. To avoid what am I going for lower casing? Case sensitivity. So I already told you we have to deal with case sensitivity issue. So because of that, try to convert all your tokens into lower case. So here what I am doing as tokenization is splitting my text given into words. So here tokenize is a function that I am defining, and it is going to take the text, the string of data that I am giving, that I have prepared and named here as text. I am giving that as an input for this particular function, and this particular function is working here, wherein you are seeing there text dot split. So text dot split method, what it is going to do, split method is acting onto your input text that you are giving. It is going to separate words automatically based on spaces. So the other exercise that we have done it on Scratch. You remember we used to check for boundaries in that particular method, like boundaries like white spaces, full stops, etc. And then we used to hold our word into an empty string till you encounter boundary, and then append that word into the list, and then you take a word out of it. So all those steps now we are not doing. We are directly applying what method here? What are we applying here, guys? Okay. So we are applying here text dot split means dot split method. Text is the name of my data frame on which I am applying the split method. समझ में आ रहा? Are you getting? So text dot split method will split the string into a list of words based on spaces. Now what I am doing? Immediately I am converting the word. So from text, what did I get? Word. Understanding? Once I have applied split method to my text had got strings of data. Automatically when you apply a split method, what you will get? You will start getting words because it starts splitting your strings based on the spaces. Clear enough? So your output would be there as a word. So now once you get that word out of application of split method, that word you want to convert it into lowercase. So that's a comprehension instruction over there wherein you are applying split function, extracting word out of it, and for that every word you are applying dot lower method. Understanding? So it saves your execution time. This particular piece of instruction saves your execution time. You are splitting your string into word, you are applying lowercasing in the same instruction. So this will convert each word in the list to a lowercase. So what that particular instruction that it is returning, it is a list comprehension. It will process each word in the text, converting it into lowercase, and then it will return you a list of lowercase words. So are you clear? So yesterday what you did as a code, here you are finishing in one particular instruction. Clear enough, guys? So what is the output after this particular step? What is the output out of this particular step? It will be, very good, list of words, all list of words in lower cases, right? Once you are done that, what am I doing here? I am taking now my data frame, okay, that I had built using pandas. To that data frame, now I am applying that particular method I just created, okay. So df text dot apply tokenize, है ना? So this particular thing will apply the tokenize function you just created to each element in the column of your data frame. Your text was into column of your data frame, no? Yeah. So it is going to apply tokenize function to each element in the text column of your data frame, creating a new column tokens with the processed text. Are you understanding? So now what are you getting? Into one column you will have your actual text. Into your other column what you will have now? Tokens. So that's how now you have built your data frame. Are the steps clear, guys? Yeah. So what did we do? We imported our libraries. We built our data set, or you can take it from any txt file if you want. Followed it up with, you build your data frame. You try to split your text based upon the spaces as words. Convert those words into lower cases to avoid any sort of case sensitivity. Then follow it up by applying that method that you have created called tokenize onto your data frame, wherein you create another column that will now have what? That will now have tokens out of the words that you have generated. Clear enough? Yeah. So you can see here, the first column was about text. I gave the text, now you can see the sequence of the data frames. The first column, it's actually column wise, you have to understand the output. It's like one column after another column. So the first column has got text, that's what we have created as a data, no? Review of movie was fantastic and very engaging, first review. I hated the acting and the storyline, etc., etc. So what does the second column had? Again the sequence starts from 0, so you have to understand it's a column. Okay, so 0 to 5, could you see the tokens there? So now the string is converted into list of tokens, list of words. Are you clear with these steps? If you are saying yes, then only I'll go ahead with the next one. Done? Yeah. Once you are done with that, if you run this code, the data frame will have an additional column called tokens, which contain list of words, all in the lower cases. So, what two steps have you completed now? What two steps have you completed now? Tokenization and lower casing. Okay. Now, I am skipping lemmatization and stemming. It's up to you. You can do that. Okay. So, either it's not always necessary, but yes, tokenization is always necessary. See, if you remember my previous class, I told you when I taught you embedding layer, I told you first step comes as input tokenization, second step would be word embeddings. But if you want to pre-process, you can also go for lemmatization and stemming and removal of stop words. Okay. So, here I am skipping those and directly I am jumping onto word embeddings. Okay. So, this is one crucial part here. So, what are we doing here? We are creating word to vector mappings, but manually. Okay. So, I told there are two ways of doing this word to vector mapping. Hai One is either you do it manually or you use what? Pre-trained vector. Could you name a few pre-trained vectors for me? Word to vec? One more I am able to hear. Little loud. Word to vec and glove. Okay. Fast text, etc. So, they are all readily available, but here we are doing it manually. So, what are we doing here? We are trying to create a function, create vocab and vectors. It's important. First we had our text, then we had our words, then we had our tokens. Now we want to build our vocabulary. Are you clear now? So here what I have named my function, create vocab and vectors. So what are the parameters that it has got? What are the parameters now? Word embedding method that you are writing require? It requires tokens, yes of course, and apart from that, the hyperparameter. What is the hyperparameter, guys? The size of the vector. In what way it is going to affect your model? That we have generated. Apart from that, we have to pass every token has to be converted into a specified dimension of vector. That dimension of vector is your hyperparameter that the user is going to define and give it to the model. What happens if you choose it as more? Higher level, I mean, if you give a higher value to it, what will happen? Very good. Although it will be able to cover large amount of words inside it, but complexity and computation expenses will be more, of course. But if you choose it to be very low also, it is not going to effectively cover all the words that are coming across in your text. So you have to take it in moderation. You have to work very carefully while choosing the dimension. Clear enough? So here by default I am passing vector size as 50. Okay? So vector size that I am choosing here is 50. So this particular function defines a particular function that takes input as a list of tokens. The name that we have given here to our list of tokens is tokens underscore list, and then as an optional vector size, we give it a default value of 50. So we are not going to change the size of the vector anywhere inside our code. Okay. Now, what are we doing now? As I told, I want to build my now vocabulary. I am going to initialize my vocabulary here. So vocabulary is a dictionary. Okay. Why? Because now I have a word and then an associated vector with it. So it's a key value pair. So it's something like what? A lookup table. You remember now? Go back, rewind in my classes. I talked about a lot about lookup tables and embedded matrix. So we are trying to build that one. So I am initializing this empty dictionary over here to store my vocabulary and its corresponding vectors that we will be generating. Once you are done that, what is the next thing? we want to create vectors for every token that we are encountering in our text. Okay, so what are we doing here? There are two for loops that I am using to iterate through my tokens. First for loop will iterate over each list of token in the token list. The second for loop will iterate over each token in the current list of tokens. Okay, now next, after that, what am I doing? Checking if the token is already there in vocabulary. Why this particular step is important?
Stores only the unique element.
Yes, exactly. What method have we used before for it? He was correct when he told to generate unique tokens. So unique tokens means to make sure the tokens are not getting repeated. Previously what we used? Very good. Set method. Okay. So here we are doing it directly. Okay. Now, this particular method will check if token is not already in the, this particular if instruction checks if token is not already in the vocabulary. And now what it is going to do, if it is not there, if it is unique, it is going to assign a random vector of specified size. What is the specified size here? 50. So it is randomly generating through NumPy. NumPy dot random dot rand and the vector size whatever that you have specified. Clear enough, guys? So vectors will be generated. And it is going to return your vocabulary, that is the dictionary that has got those key value pairs as unique tokens and its corresponding vectors. Clear enough? Now, create vocabulary and word embeddings. So now I am applying that to my data frame. Okay. So create vocab and vectors, I am using it. I am passing my data frame of column, not text, tokens. Now my data frame has got two columns, no? One is text, one that we have created just now. What was it? Tokens. So I am passing data frame of tokens, the column, into my function that I just now created for word embedding, and I have specified my vector size as 50. Now the vocab dictionary will contain each unique word from the tokenized text as keys and their corresponding random vectors as value, as we just discussed. This is how the output looks like when you will run that particular cell. So every word will be what? Will be having of size, a vector of size 50. So if you could see there, the is the first. I don't know, this laser is not working. The is the first word. Array is starting and they are like elements 10, there are elements like 50 elements for the. Then the movie array is starting over there, 50 elements for that. So do you remember our first sentence there? The movie was fantastic. So it is taking the movie was and so on till the last word inside your text. So this is just a snippet of the output that I am producing here. So are you clear? That's how you randomly generate vectors. So now what is required? The is not required. Now the index related to the will be required and its lookup. What is its lookup? The random vector that is generated. Now the machine will be working only with the index value and vector. Index value and the vector. You might think text processing is happening, but inside only vector processing is happening. Now machine is able to work with string data. Clear enough, guys? Yeah? Now, once you are done with those pre-processing steps, these were all pre-processing steps, no? So, the first step was, what did we do as our first step, guys? Imported our libraries. Second step, I'm not able to hear anything out of here. Create your own data set. Third step, converting the text into words, then tokenizing and lower casing. Follow it up with. Can I go for lemmatization stemming if I want? Yes, I'm skipping. Next crucial step. You want to build your vocabulary. How do you do that? Through embedding, word embedding. What is the hyperparameter involved? By default, how much we are giving? What does after embedding, what would be the output? So it has got all key value pairs having token and its vector. That is randomly generated. Again, randomly generated. I am not using any pre-trained vectors. So text pre-processing is over, guys. Now we are going in depth. We are trying to prepare this particular data set now for word prediction. So word prediction ko preparation mein there is one more step that is left, as I told. Machine will require indices. Okay. So till now you have got still those key value pairs. You want indices. So we are still trying to prepare our data set, wherein what we are doing here, we are trying to prepare data set for word prediction. So you are trying to build another function called prepared sequences. This prepared sequences, how many parameters it is taking? What are the 3 parameters? It is taking tokens that are generated and vocabulary that you just built. What did vocabulary hold? Tokens and their randomly generated vectors. And what is the third one? See, very, very crucial thing that I am teaching. Please understand what is this third parameter. What do you understand it would be? Context size. Very good. So it's like you are giving a window to the context. It's a context window there. So context window means what? Minimum of how many words would be used to understand the context of your input and try to predict the next word out of it. So here minimum how many words would your model take? 3 words. And try to generate or predict 4th word. Clear? So what is this? Function definition is prepare sequences, defines a function, takes a list of token and a vocabulary dictionary and an optional context size. By default, here it is 3. Now, what is this context size that I was talking on? Context size is a parameter called as context window. Okay, so it refers to the number of surrounding words used to predict the target word. Abhi now terminologies are important. Context words, target words. Context words like the movie was fantastic is what was there. So at least I should give input as the movie was. Context word is the movie was. Minimum 3. So the model will predict was. If I write the movie was fantastic, the model will predict. Okay. If I would say, write the last 3. Fantastic, but also dash. So it will take, even if I am typing, more than 3 words, the movie was fantastic, but also dash, it will only take the last 3. And it will predict, it is going to predict me engaging as per the input that is present. Are you clear? So context window is an important parameter here. It refers to the number of surrounding words used to predict a target word in a word prediction model. So target word is your output. Context word is window that you are taking from your input sentence to predict the output based on the context. Clear enough? Next. Essentially, it will determine how many previous words you can consider as context to predict the next word. That's what I have taught you. Okay. Now, for context size equal to 3, this is for your example as I just told. For an example, after tokenizing one sentence, let's say the sentence was the quick brown fox jumps over the lazy dog. So it will tokenize And if you are trying to, let's say, predict fox, the context should be 3 words before the fox. So what should be the context 3 words before the fox? The quick, brown, should be the 3 words to be given, and the target will be fox. Similarly, if you are trying to predict target as what it will be? Jumps. The target for an example is jumps. What should be your context words? Fox, brown, quick. So 3 context words, 3 words that are before your target are your context words. What you are predicting is your target word. Clear enough? Yeah. So now we are building our data set for this. Now here, you slide this particular context window. What is our context window for our code here? Context window is 3. Size here we are given as 3. You will be sliding this particular window across the entire sentence. Why? Because anything can be asked by the user. So take that context window, slide through your entire text, 3 words at a time. Try to predict the 4th word, because I have given your context window as 3. So slide this context window of 3, the kernel for an example of 3, and slide it over through entire your text unless and until you get all possible input-output pairs out of it. Are you trying to understand what we are doing here? Yeah, we are building our own data set in the sense so that it predicts every 4th word given any 3 context words. So, you slide this context window across entire sentence to create multiple input-output pairs for training your model. So, from data that you got, you have to change it into a format suitable for training your sequential model. So, what is the format suitable for training your sequential model? Input-output pairs. How do you get that input-output pairs? First, take your text, take your data, tokenize it, embedded, pass it through your embedded layer, create word embeddings out of it. Once you have done, you have to select your context side, slide that context window throughout your data, generate every possible input-output pair. For every 3 words, there should be an output. For every 3 words, there should be an output. So, you are creating these multiple input-output pairs, gather them enough so as you will use that to train your model that you will be now building ahead. Clear with the process, everybody? If you say yes, then we will go ahead. Right. So, here for an example, as I told you, the quick brown is your input value, output value is fox, and so on. So, such pairs will be generated. So, here, what do you require? You require to pass inputs as token, you require to pass your vocabulary, you require to pass your context window to this particular function. Now, what is happening? Acha, I forgot this point. You can ask me why context size was 3. Can we change it? Yes, you can. So, how do you select it? Hai? So, I would say if you ask me that question, context window will be selected again based on type of application you are doing. So, now you understand what all things is your model performance based on. What is the first thing that you have observed? Vector size. Sequential model only I am restricting. So, the first thing that was affecting your model was vector size. Now, this is the second thing. Okay. So, what is that second thing? Context size. How you would select your context size? I would say it will be based on application. So, for a smaller application like word prediction, I prefer it to be around 3 to 5, not more than that. Okay. So, a larger context if I am taking, it will capture more information, but it would be computationally more expensive. Okay. For a smaller context, it will be more focused, but may miss some broader sentence level relationship. So, you always have to make sure there is a good trade-off between them, and then pick up a certain value that fulfills your task. So basically, for all these smaller models that we are building here, we will try to choose it anything between 3 to 5. So here I am taking it as 3. Now, there will be 2 things that this particular method that I am building will return. Okay, what it is, there will be 2 lists. First list is named as X, second list I have named it as Y. The X list will convert all the context words into their vector representation, and Y list will contain index of target word. So now understand, what are we building? It's like a table. You know, the first row will have first 3 words, fourth one, the next one will be your target. So target means you are not storing the word, because now we are not working with words. We are working now with numericals. As a machine, you have to give it numericals. So what are we doing? We are giving context vectors, and what am I getting as my output? One more, target index. Try to correlate what I mean to say. Okay, I am creating this particular function. I require 2 things out of it. I am still preparing my data set. I didn't start building any model yet. So what am I doing? I did tokenization, I got my vectors, everything correct. But I have to train my LSTM model. It's a sequential model. For that I have to build necessary information to train that particular model. How it will train? By creating input-output pairs. So from your given data now, I have to convert it into input-output pair. How will be the representation? It is not like input words ho gaya, 3 words de diya, and output predict kar liya. No. You will be converting 3 context words into context vectors, store it in a certain list. Its target would be another word, na? Not word, location of that word, index of that word. समझ में आ रहा? So your input is going to be what? Vectors as your context. Your target is going to be what? Integer as an index. Make sense? Yeah? So the function that I am creating now is going to return me 2 values, 2 lists. है ना? First list is X, which contains context words, which is converted into their corresponding vector representation, which you will extract from vocabulary that you have created. Y will be containing the index of target value in the vocabulary. Clear enough? Now we will quickly see how do we build it. So once I have defined my function, what am I doing there? What am I doing there? Come on. I am going to initialize those lists, because that's what I am expecting as my output out of this particular function. Okay, so I am going to initialize my list. In order to, what are you going to do? How do you create these 2 lists, X and Y? Once you have defined your prepared sequences, you are going to take up your data frame, which has got now tokens. So data frame has got 2 columns with you. First column is text. Now we are not working with it. We are working with the second column, which has got tokens. So you will iterate over all these token values to generate context target pair of each sentences. So how you will create? The movie was. This was context. So eventually relevant vectors of them will be taken into that input-output pair. The ka vector, movie vector, was vector. What is stored in target? Fantastic index. Let's say if it was 3. Okay. Next context window. Movie was fantastic. Target but. Then slide those context windows. Generate your input-output pairs like that. And keep and store it inside your list. So first 3 words, that's your target. Next 3 words, that's your target. Next 3 words, that's your target. Consecutively, you are sliding and calculating your input-output pairs. But again, I am reminding, for your understanding, it is words and location. It is actually vectors of the context words and index of your target word. Clear enough? Right. Now, so now, as I initialize those lists, I am going ahead. So what are you doing here? Context words and target words. So you have to select your context words and select, you have to write a mechanism to take your target word. So what is context word? It is purely based upon the context window. What we have given as that? 3, context size or context window. So what it is doing? You are extracting the context. Out of all the tokens, you will extract a list of context size tokens starting at an index of I. So I started it. For loop mein dal diya, keeps on extracting. Then target word. It selects the token immediately following the context as a target word. Yes or no? So the first 3 words come into your context list. Immediately following next word will go to your target list. And then take a for loop. Keep on sliding, get your results. Clear enough? Next, what we are doing? After you have extracted one pair of context words and its subsequent target index, you would like to append that to your existing list. So that's what I am doing there. You will convert the context words to corresponding vector using vocabulary. See, what is this vocabulary? Vocab of word. Where did we use this? Where did we use this vocab of word? Very good. We created a dictionary. You remember? So from there we are choosing our vocabulary. Okay? So see how the process is. It's a little bit complicated. You'll have to remember everything. So if you understand transition that we are going, it is easy for you to recollect and reproduce the same tomorrow. What did we do? How is the transition? Text, data frame column containing tokens. From there creating keys and values, building vocabulary. From there generating vectors. Now selecting context size. Creating input-output pairs. Input will be having context 3 words, 3 context words which you will be sliding on, and output contains index of the target. So first 3 words, context vectors, next immediate word would be your target index. Like that, keep on appending, build a new list out of your vocabulary that you created. Clear with the transition? Yeah. Now, obviously it is going to return. It is going to return. But what am I doing while returning? What am I doing while returning the values? Converting it into NumPy array. Why it is needed? Why is it needed for me to convert that list into NumPy array? Come again? Instead of the, I'll tell you. See, vector is required. First thing, vector takes memory. And vector is required when you are working with internal mathematical calculation. When you are trying to figure out the context, as I told, the model is a neural network. It will take the input as the vectors to determine the context. But once you are giving the output, you require only the next word to be predicted. You are not performing any heavy mathematical computation over there. So what you require is the location of the output. That is represented through index. That's the reason I am avoiding that computation to take a vector and then revert it back as an output. Simple I require is a word for prediction, so I am storing it as an integer. Clear enough? Yeah. So I think that was a valid question that he asked. Why output is an index and not a vector? So clear enough? Yeah? So I am converting that into an array. Now comes application of this function that we built. So you have to pass now suitable. See again, when I am building these functions, you have to build it. Based on your change in the inputs, this particular part will change. Application part. So try to be more focused when you are doing exercises tomorrow. Which one by default you have to create, which one you have to change and tweak. Please understand. So let's apply this function that we have created. You create sequences for all rows in the data set. I have kept here context size by default as 3. Initialized my empty list as I needed. Now I have to choose from where I have to take the tokens. So I am going to take tokens from where? From my data frame column tokens. And I created my vocabulary out of it. Yes, I have already done it before and I stored it into a dictionary called vocab. I am using the same here. See, this is important, guys. For every model, you require training. So you are training your LSTM model that you will build next with this X and Y. X and Y. So this was very crucial what we learned today. How are you getting X and Y out of a text data? So this was this elaborated process that we have done to get your X and Y. Generally क्या करते थे तुम लोग? You used to take a CSV file, a test train split, getting X, Y, train the model and go off. But here things are different. You are generating that X and Y out of that sequential data. So this is a very big process that you have learned today. Understood? So now what am I doing now? My aim is to get X and Y out of applying the method I just created, prepare sequences, wherein I am passing there 3 parameters. One is tokens. Tokens is your data frame tokens that you are passing. One is vocabulary, which you created a dictionary already way ahead. One is context size, which you are assuming here to be by default 3. All 3 you will be passing now and getting your data set prepared, wherein now the output here will be returned as X and Y. Now, I am doing one more important thing here, guys. What is it? Why? Why am I using here extend? I can directly use something else, na? I can go for, okay, let's see that in detail. I think this I have explained you. I was talking on this. Why am I using their extend in place of append? What is different? Have you ever heard about this extend? So why am I using here extend and not append? Yes. Correct. So if you see here, if we use append, then it would add that entire list of X sequence as a single element. It will not add as an extended elements. Got my point? So that is the reason now here it's very, very crucial that you use extend rather than appendation of list. So I'll quickly give you one example. There are 2 lists here, 1, 2, 3, 4, 5. What happens if I take append and extend? Look at the output. So when I am using 4 and 5 as an append, that list itself is appended as a single element. What is happening when I am using extend in Python? Now it is added element wise. So what do you want? I want to be added element wise. So that's the reason. For my input output pairs, I am using their extend. Clear, guys? Right. So after I got my X and Y also, my list, I am trying to extend, use an extend method onto it. Of course, later I would convert that into NumPy arrays because of heavy computations that are required. So it returns the prepared sequences as 2 NumPy arrays. X will be the context words which are represented as vectors and Y will be the index of my target word. Again, X will be vectors, Y will be index. Clear? Okay. Let's just take one sample sentence and understand what we have written. Hai So I was talking on this quick brown fox. Hai So same tokens, quick brown fox jumps over the lazy dog. So what did we do? We first, guys again, please don't miss this step. It is a summary of what we have done. Okay? A little different than the example that we have taken. Smaller sentence so that you understand better. So what was the context? What was the number of tokens here in this particular example? So what are they? The quick brown fox jump over the lazy dog, 8 tokens starting from 0 to 7. Now, what will happen for I equal to 0? That for loop I am explaining. Try to understand. What will happen when I is 0? What is context size? What is context size? What is the range over which I have to iterate now? What is the range? I is 0. The context is from 0 to 3. 0 till context size. So, what would be your context? The quick brown. 3 words in your context. What would be your target? 4th word. What is it? Fox. Okay. So, X of 0 will be vocab of the, vocab of quick, vocab of brown. Goes to your dictionary that you created and extracts the information out of it. What it will extract? 0, 1, 2. Index of your context words. And Y of 0 will take the index of your target word. Now those index, you will go and convert that into vector, use context word vectors, and index you keep as it is for the target word. Okay, so this for 0, 1, 2 context or its relevant vectors, the target would be 3. For 1, 2, 3 as your context vectors, the target would be 4. Like that you are creating your input-output pairs and generating. This is called preparation of your data set. This I was talking on. Clear enough? So if I am talking X as an index, actually it is internally taking X as a vector. But because you are supposed to predict only a word, so I suppose to save memory, you can just generate an index, co-map and get what is the word for prediction. That is the reason index for target, vector for input. Clear? Right. So this is your Y. Now, coming back to our example. So we were able to get your X and Y that you want to train your data. Okay? Now what are you doing? Your next step is to convert your data into tensors. What is the need? What is the need? Why do you require tensors here? Brainstorm, guys. Everything I need not answer. You have to tell me. At least try to figure it out why. Where you can work with multi-dimension data. है ना? Tensor will actually help you to work with multi-dimension data. Why, you can ask me. So, do you remember when I taught you word embeddings, I taught you sentences will be given to the machine in batch-wise. Did I tell you or not? When you are dealing with large amount of data, input sentences will be piled into batches and given. So now output should also come batch-wise relevantly, thereby increasing dimension. So to work with multi-dimensions very easily and effectively, you utilize tensors. Okay. So here I am using data here that I have produced, that is X and Y, and I am converting that into tensors, which will help me in so many ways. The first is it will support computations on GPUs, faster computations. It will be helpful to support automatic differentiations, gradient calculations are made easier, and compatibility, because most of the platforms globally, they make use of tensors. To make your piece of code globally compatible, try to convert that into tensors. Clear enough? That's the reason you are converting them into tensors. Important part. What are you doing? Now converting your PyTorch center tensors. X tensor I am creating, passing my X value. What is the data type that you could see? What is the data type for X? Float. What is the data type for Y? Y? So Y is an index, it is an integer, 64-bit long is sufficient enough to take, so we are taking long. And float 32, majorly all of our computational operations are done on 32-bit floating point numbers. So that's the reason your vector have been given a data size of float 32 tensor. Clear enough? Clear enough? Yeah. Now comes the major part. So till now what you did was to take your text, make it suitable for training your LSTM model. It was just pre-processing parts that you were doing. Now you will create your model. What model are we doing? LSTM model. First step is clear, guys. Are you clear with what we did in our basic pre-processing? Making a sequential data come into the format that is actually acceptable by any sequential model, whether it be an RNN model or an LSTM model or a GRU model or any other NLP model that you are taking. Okay, once you have done that, take a grip on your model now. So what is my model? LSTM model. So I have to define my LSTM model for word prediction. That is my task. So obviously I am using PyTorch. So I am here creating or defining my class called word prediction LSTM. My class name is word prediction LSTM, and it will be defining me an LSTM based neural network for word prediction and initialize the layer through an init method and the parameters of the model. So what are you passing as parameters in that init method? Self is okay, self-instantiating, and then input size, hidden size, vocab size, crucial parts, right? Again you came back to RNN part. Input size, hidden size, and vocab size. Okay, so let's see. Input size. So what is input size? It is typically the size of word embeddings that you want to work with your LSTM. We already knew, we gave it as say 50. Okay. Hidden size. What is the size of hidden state in the LSTM that you want to design? Vocab size. What is the size of vocabulary or the number of unique words that it will be capable enough to work with? So all these are your parameters of your LSTM model which you will be passing. Next is what? You define an LSTM layer. Model was LSTM. Inside the model will be several layers. So first layer that I am designing is of LSTM layer. The next would be obviously a dense layer, that is my fully connected layer. Okay, linear transformation ke liye. Okay, so LSTM layer, here you are giving and passing obviously input size, hidden size. Now important here, batch first equal to true. Batch first equal to true. Important here while you are coding also. Suppose you are working with big amount of data wherein you want your sentences to be clubbed as batches and to be fed to the machine. Then you have to make sure you have to give here batch, what is it? Batch first equal to true. The moment you place this batch first parameter as true, what is going to happen is, it will give the output tensors and the input tensors shape changed. It is going to give it in terms of batch size first, sequence length, and then features. So once you make that particular thing true, it is going to affect to the dimension of your input and output, wherein first will be the batch size, followed it up with its remaining parameters. Clear enough? Right. Next, what we are doing? Linear layer. So it is nothing but a fully connected layer which is going to map our hidden size to the vocabulary size that we have defined. This particular layer will convert the hidden state from LSTM to the predicted word indices. So when you are building your LSTM model, first you create your class, you define your class with your specific parameters of input size, of hidden size and of the vocabulary size. Then you start building the model by first creating the layers. The first layer that we created is of LSTM layer. So inside that LSTM layer, you are supposed to give what is the input size, what is the hidden size, whether you want your input and output dimension to be reflected with batch. Okay. After that, simple linear layer which is fully connected layer which will be mapping that hidden size to your vocabulary size, and it will try to give out the index as your output by running through your LSTM model. Clear enough? Clear with your model strategy? Now, if you have built your model, now is the time that you take your input, hidden sizes and everything and go for a forward pass and then a backward pass. That's how we work now, normal neural network. So same, now that we have built our model, let's go for a forward pass. You have some doubt? Now, so I'm defining the forward pass here. So, forward pass means what is happening? What is happening in the forward pass? Come on. Trace that particular piece of code, I'll give you an explanation. What do you think is happening? What is happening in an LSTM, guys? You are trying to get the output through every hidden state for every timestamp. All the sequences of the words are coming. You are trying to predict the next one after another by calculating the hidden steps, hidden states from one state to another, from one layer to another. So what we are doing here is, input is X. Yes or no? From X and Y that we have created out of our data, we are taking X because what you require as an input, context vectors. What you require as an output, fourth word index. Yes or no? Are you with me? Are you in sync with me? What is your input to LSTM? Context words, any three in between randomly, in sequence but. And you should have your output as index of the target word. Yes or no? So, here input to the LSTM model will be what? X. 3 word vectors you will give. X, you will pass. Now, you will pass X in the forward pass and then you will be, X is actually in the form of sequence length, input size, but apart from that, the first prefix, which is your batch size, because you remember I gave batch size was true. So, X is of the shape, batch size, comma, sequence length, comma, input size. So, batch size is the number of sequences in a particular batch if you want to give. Sequence length is the number of tokens that is present inside a particular sequence. Input size is the size of each word embedding, that is size of each word vector. Now, LSTM layer. What is going to happen in the LSTM layer? This LSTM layer takes the input as X. X is taken, given to LSTM layer inside your model. So, LSTM layer gives you 2 particular outputs. What are they? The first output is the output of LSTM for every time step. Hidden states, internal hidden states. Do you require that? No. We don't need. What we need is the end what output it is giving, what word it is predicting. Okay? For that reason, guys, you can see that when I am applying self.lstm, left hand side we have kept an underscore. Underscore means ignore. Okay. So the first output that you get when you apply X to an LSTM is an ignore. That is actually the internal hidden states that you are getting, which you don't require. That's why an underscore. We are not trying to store it. What is the second output? Second output is in bracket. That means what is it? Bracket. Tuple. It's a tuple. So tuple has got a hidden state inside it and the cell state. Again, for this you have to understand, go back to the architecture. I told you there are two states of LSTM. One is hidden state, another is cell state. So here the first underscore there not captured is the output of LSTM for every time step in the sequence, which we are not capturing. The second output is actually a tuple which has got a hidden state and a cell state. Cell state anyways we are not using here. Why do we want what context it is storing? So again a underscore there. What is our major thing that we require? What is the final hidden state that we are getting? So for that reason there be very specific. Once you apply input to LSTM layer, output out of LSTM are actually two. The first, at every time step its output, which we are ignoring clearly by using an underscore. Second is a tuple having hidden state and cell state, out of which our requirement is only hidden state. That's why cell state is again given an underscore to ignore. Internally it stores, that is through cell state. We are not trying to read the cell state. Unnecessary, it will give computational cost to us. We require, after storing and calculations, what is the fourth word that it is predicting. So our focus is there onto the hidden, not onto remaining other parameter. That's why they are given their underscores. If you want, you can actually work on it, but here we are ignoring it. Okay. Now, once it has worked on to this hidden state, what do you require now? As I was telling, I just told this, the underscore is used to ignore the output that we are not interested in. One more important thing guys here that I forgot to mention. The shape of this particular layer would be number of layers, comma, batch size, comma, hidden size. Here how many layers of LSTM are you using in this code? One. One LSTM and one fully connected, a very basic model we created. So here number of layers will be 1 and hidden will have a shape of 1 comma batch size comma hidden size. Please try to understand. Okay. Now see here what we are doing, hidden of -1. Why do I need that? I require only the last hidden state. Why do I require only last hidden state? Because that's my word that I am going to predict. I mean that's the index that I actually need. Okay. So hidden of -1 selects the last hidden state of LSTM for each sequence in the batch. The reason we are using hidden -1 is that it corresponds to the final time step in that particular sequence, which is typically considered to have captured most relevant information about entire sequence. That's your answer. So we require the most relevant information. That's why we are not capturing all the hidden states and internal cell states. We require only the latest hidden state for predicting the output that is need of the hour. That's why we are concentrating on that. Okay. So hidden of -1 that you are taking has got shape, batch size, comma, hidden size, and that you are taking as your output. Now, now what are we doing? We will now define our LSTM model for word prediction. Okay. LSTM processes the input sequence, extracting hidden states at each time step. Last hidden state is taken as the representation for the entire sequence. Fully connected layer will map the last hidden state to the vocabulary space. Important. Technically, that vocabulary space are called as output logits. What are they called? Output logits. What do you understand by that? Okay. I'll go back. Here, fully connected layer is going to map the last hidden state to vocabulary space, giving output logit. Output logit means probability that out of all these words, this would be my classified output, but not exactly probability. You still have to get a probabilistic output. That you will do by applying softmax function. Before applying softmax function and clearly taking out probability, rough figures you get, telling this could be the output, major values falling. That is called as a logit. So till here you get your output logit. But final classification you will done by applying softmax function and getting proper probabilistic output. Because output logit can roughly give you, it cannot accurately give you the value or the probability. Okay. Now, initializing your model is your next step. Once you have created your LSTM model, you will initialize your model. Now I am applying what all I have created. Input size is equal to vector size. Yes or no? Vector size, how much did I give? How much did I give throughout? 50, no? That it will take. Hidden size, you already know this when ma'am taught you about RNN. You will take hidden size as 64, 128, 256, basically 2 power n order. So here I am choosing my hidden size as 64. User specific. Okay. So input size is obviously my word embedding size that I have decided. Now we are talking input as relevant to LSTM. Don't get confused. That word, preprocessing, everything is done. You got your X and Y. Now you are diving into model building. Here input is different. Don't get confused now. Again I am telling. It's a bit complicated, but try to understand the transition how we are moving. We created X and Y now to train our LSTM model. LSTM model mein we defined LSTM layer. LSTM layer should have inputs as hidden state size and input size and also vocabulary size. To work onto it, to get your latest hidden state. That will be mapped to your vocabulary size using your fully connected layer. These two layers work together to give you your final output. Now you created that from scratch. Now you are trying to actually figure out your code by passing suitable values. So I told you LSTM layer takes hidden state, that is user specific. Here I am defining as 64. You have to give it in the order of 2 power n. 64, 128, 256, 512, etc. Here I am choosing 64. Okay? Input size is equal to your embedding size, vector size. That by default we pass throughout as 50. It will take as 50. Vocab size, length of your vocabulary. You built your vocabulary, no? Key and a value. Dictionary you created. So length of that will be taken as your vocab size. Now you are applying your LSTM model and taking the result into a model. Now, once you created your model through LSTM, what will be your next step? हो गया यार, forward propagation and all. You want to see the moment I use an LSTM layer, na, I am invoking that LSTM layer means I gave forward pass values. Backward propagation, changing everything internally it will do when I run this particular model. Forward pass में I passed the parameters that are required to initiate that LSTM layer. ठीक है ना? Now what to do? I created my model, guys. Train that particular model and then evaluate that particular model. Okay? So the next step would be, once the model is initialized, you want to train it, but before that, you will choose what loss function, what optimizer, on what basis you want to test this particular model, है ना? So defining a loss function, I told you the output will be roughly logits. What is logit also I told you, okay? So defining a loss function to compare predicted logit to true target word. So this output logit is roughly your vectors that you have generated. Your output logit will now be compared to your context vectors. Okay, to your word vectors, sorry. Defining a loss function, here we are using cross entropy loss function because it is a multi-category classification, है ना? Now, choosing an optimizer, we are choosing Adam to update models parameter. We are feeding in batches of the data to train this particular model. So again, loss function. What does the loss function do? Quickly. What does the loss function do? Difference between predicted output and true output. Here, predicted output is your output logit. True value is the vectors that you already have stored inside your model. Huh? You are using cross entropy loss function for the same because the output is a probability distribution over several classes. Optimizer will update all your model parameters based upon the gradient of your loss function. Here we are using Adam. What is Adam? Adam is a short form for adaptive moment estimation. It will compute adaptively all the learning rates. You are not giving any fixed learning rate there like you used to pass LR. Here you are not giving any fixed learning rate. Adam is an adaptively changing the learning rate suitable enough to get you an optimized value. That's the beauty of using an Adam optimizer. So here if you say initialize, if you want to control your step size, you can give a learning rate, let's say 0.01, it should be small enough. But adaptively, it will change your learning rate to give you an optimized results. So, as I told, why Adam optimizer? Adaptive learning rates are there. It combines the advantage of both SGD and RMS prop. Adam is very popular optimizer because it is going to combine the benefits of both SGD and RMS prop. SGD with respect to the momentum of SGD and RMS prop with respect to smooth optimization path. Both of things will be clubbed when you are using an Adam optimizer, and it is default popular choice for many neural network applications. Come on. Now start training your model. Okay, you built your model, you define loss function, you define what optimizer you are using. Now training loop, number of epochs. What is this number of epochs? How many times you want that particular thing to pass through your input and generate your target. Okay, so number of epochs I am setting as 30. You can change that if you want. For every epoch, you will train your model, you will resend we will see everything in detail, okay? What is the requirement? The first part, for every epoch, you will train your model and you use a zero grad function in your optimizer. Why? What is the requirement of using a zero grad? Zero grad. Already this has been taught to you. Zero grad. Yes, it will clear any old gradients that were present so that lot of memory is not utilized in accumulation of these gradients. Okay, that is the reason you will use here zero grad, resetting the gradients. Forward pass mein, taking the model, passing tensored X that we have created, storing the outputs, checking for loss, okay, calculating the loss using criterion outputs Y tensor. Criterion mein we have defined our loss functions, okay, in the criterion method. So that's what I am calling here and generating my loss. Output will be a tensor, guys, important. Output will be a tensor of shape, batch size, comma, vocabulary size here, once you pass extensors. Okay, so you can see, I guess I've already taught you about loss function. Now we are going for that backward pass ka thing, just simply, computing the gradient of loss with respect to each parameter. Automatically it is done inside an LSTM layer, and the gradients are used to adjust the weights in the model. Till now, we were more focused on updation of these weights in bias, but now we are keeping that process automated. Here we are just passing what parameters are required for smooth running of forward pass and backward pass. And after computing the gradients in back propagation, optimizer will update the model parameters to minimize the loss. For that, you have to use optimizer.step. Okay? After forward pass, backward pass, use optimizer.step to update your model parameters, updation of model parameters. Now, this was the thing. So if I have chosen 30 epochs, I could take a snippet till 25 only if it is visible, and I tried to print the loss of it. So you can see what is the loss that am I getting. The first epoch had a loss of 3.4992, and by the end I entered 25th, it gave 0.3723, and the 30th epoch was even more less. So back propagation was working, wherein it changed the weights and the biases, and the output logics that were produced were matching to the vectors that were present. Clear enough? Model with reduced losses have been built. How do you check for your output now? Till now we used to stop at this stage, है ना? अभी हम क्या करेंगे? We will learn about an interactive way of prediction. We will write a prediction function. I'll explain every step. So prediction function, because as a user you require to predict. You have to give context word. It has to show predicted output, है ना? So important, guys, for your tomorrow's exercise. Okay. So prediction function. What are you passing as parameters? Context. So what is the context? Minimum I have kept how much? So at least 3 words with spaces I should give to the machine. Yes or no? At least 3 words I am supposed to give to the machine. That is my context. What is the next parameter? Model. Right? What is your model? It's your trained LSTM model. Vocab. That dictionary that you have created for your vocabulary. Context size. Number of, see, input sentence that I am giving, I can give a maximum of 6-7 words also. But there is always a minimum that I am supposed to take. What is that minimum? Throughout the code, I have selected context size as 3. I am retaining it here. So even though I give a bigger sentence, say 5 words, it will consider only 3 words, last 3 words as context, and give me the 4th word as the prediction. Are you clear? So tokenize input context. Tokenize input context. Obviously, when I am giving context, machine has to understand what context that I am giving. So suppose I was giving the movie was fascinating and. So all those words have to be broken down and understood by the machine as context vectors. If I understand that as a context vector, then I will give you the 4th index of the word that has to be predicted. Understanding? So I am tokenizing my context or the input context words that I am giving to the machine. If suppose it is less than the minimum context size demanded, it has to generate an error. So what is the minimum context size that I gave? 3. Suppose if I am writing to the machine the movie, it is not going to predict anything for me. It has to give me an alert or an error. So what am I printing? Raise a value error. Context must have at least so and so words depending on your context size. So first thing that is done. Next thing, suppose if I am giving very large sentence as my context, say 7 words. But out of those 7 words, it should take only 3 because we have built the entire model based on 3 context words. So even now, even though I have typed 7 words there as a context, it should take 7 minus 4, only last 3 words, and then generate the 4th word as the output. So that's what I am going to do here. Tokens is equal to tokens of minus context size. So last 3 words will be, last context size words would be my actual thing that I am taking and predicting the output. Next, convert those tokens into vectors so that machine can understand it to take it as an input. So for that I require my vocabulary dictionary wherein I have all key and its corresponding vectors. From there I will convert all my context into vectors that will be passed to my LSTM model. Now my LSTM model will take those context vectors, tries to generate what is the next word into the prediction, gives you the output index of it. And then you have to again co-map it to the word and generate that word as an output. That's what we are doing. Convert PyTorch tensor, add batch dimension. Very, very important. Because I told you what is the dimension of your LSTM. It is in terms of first batch size, because there we mentioned batch size was 2. Anna? So batch size here is 1 because you are passing only single layer LSTM. Batch size is 1. So input tensor is torch tensor of shape 1, comma, context size here is 3, comma, input size is 50. 50 vector size. 1, 3, 50 is what you should get as your dimension. Now, once you have trained your model, you will go for evaluation of that particular model. Make the predictions with no track gradients in order to increase the speed and reduce the memory. Okay, no grad. We are making predictions with no track gradients. Make the prediction. Output will have the shape 1, vocab size. Here you are using argmax to find the index of the word with highest logit. So there will be certain predictions throughout. Check for the word which has got highest rough prediction logit. Convert that into the index of the word. And then you are going to take that index, search that in the list of your vocabulary and return back the predicted word. Clear with it? Yeah. Okay? See, I'll go it again. After evaluation, you are predicting with no grad. Okay? After that, output would be when you apply the model, when you get the predictions through that particular model. I told predicted index would be argmax of my output, and that particular, it finds the index of the word with the highest logic, that argmax part, and dot item is done to convert it as an index from that particular vector, because at the end what you require is one word. Target word is always stored as an index. So once you get that index, you will use that particular index, searching it in the vocabulary keys and getting that particular word as your prediction. Clear enough? So let's see. Okay? It will return you with your predicted word. Can I? Yeah. Now we are doing an interactive testing function wherein I am printing, enter a context sentence to predict the next word. I am predicting my context, enter a context sentence to predict the next word. Now, when you input the enter context, first you have to understand that what the user is entering. Here I am keeping an option. If the user don't want to run, he can give exit and it will terminate. So the first step that I am writing here, if the user is to check whether the user has written exit. Otherwise, it continuously keeps on running that model asking for next word prediction. So first, if it is exit, then it is going to terminate. Next, if it is not, you try to predict the next word out of the model. Or else, if at all the entered context is very small, it will have to raise an error. So that's what I did it. It is completely optional, by the way. Now, this is it. So I am now running my model. It displays something like this. Enter context. Do you remember our first sentence in our text? The movie was fantastic. So I first wrote enter the context as the movie. What did it answer? Context must have at least 3 words. Ensure the context has at least 3 words. So I again enter. I wrote the movie was. Can you see what was the prediction? Fantastic. Now, I gave a bigger sentence. The movie was fantastic and very. What is the prediction? But it could internally take only 3 context vectors and predict you the output. Clear enough? So that was your overall building LSTM model to predict next words. Suppose I am writing exit, it gives me whatever message that I have given there. M stops the model. Right. So the model is the basic thing that I want to explain you today was how to pre-process your text, convert it into X and Y and build a suitable sequential model. Clear enough? So quickly take a break, come back for quiz.
All of you, those who have not yet submitted at this moment. I'm switching it off.
Alright. So our next topic for today is about attention mechanism. Okay, attention. All of you, we are going to study about attention mechanism today. Okay. So what do you understand by attention? So whenever even to a small child or from your school days onwards, we say attention. And then what you would do?
Immediate response.
Response, you become alert. You concentrate basically on that situation around. Yes or no? So when I say attention, what is happening? You are trying to concentrate around the situation that is present across you. Correct. So today we are going to see what is this attention mechanism in your NLP tasks. Before that, I would like you to introduce to sequence model. Have you ever come across this term? Sequence to sequence model. Sequence to sequence model. Anybody? Okay. So sequence to sequence model are nothing but they are a type of neural networks only. Okay. What are sequence to sequence model? They are a type of neural network only. It's an architecture that is used to transform from one sequence to another sequence. Okay. For an example, if you give Google, it's like, hi, my name is. So, it will translate in Hindi and say, Namaste, mera naam hai. Okay. So, it is going to give a proper sequence input it is going to take and it is going to generate you an output which is also a sequence. Okay, so that's a basic sequence to sequence model that I can explain it for you. Taking input as a sequence and generating output as a sequence. So a neural network architecture that takes input as a sequence and generate output also as a sequence is nothing but a sequence to sequence model. Basically like a translating from one sentence in one language to another one. Now they are particularly useful in tasks such as machine translation, text summarization, conversational agents that we call as chatbots or your chat GPTs, etc. So you can see the applications of your sequence to sequence model. The first one is machine language translation, where a sequences in one language is translated into sequences of another language. And text summarization. What happens in text summarization? Your last minute batting in your examinations, what do you do? When you don't have sufficient time to go through the entire answer, what do? You scan for important points. You know? So what are you doing? You are attentively going through that text and picking out some important point that could give you an entire gist or summary of that particular concept that you are reading there. है ना? So that is nothing but text summarization. Okay. Next is chatbot, which is nothing but your chat GPT or any other chatbot mechanism that you are using. What will happen? The customer will write sequences of sentences. You are going to trace out important keywords and give that relevant answers again in sequences of sentences. So sequence to sequence modeling applications are these. Few of them I have mentioned. What exactly does a sequence to sequence model have? As I told you, it is again a neural network architecture but has got encoder and a decoder. Let me be very clear here, guys. I am not going to explain this sequence to sequence modeling again in depth. I am going to teach you the concepts which I am going to take for attention mechanism. ठीक है ना? So for transformer building purposes and all, when I am building a transformer, completely it will be through encoder, decoder and attention. So here I am explaining sequence to sequence model with respect to the information that I require for teaching you attention mechanism. Are you understanding? So that's my idea for today's class. So sequence to sequence model as a gist and a brief understanding you should have. Before understanding that, I don't want you to dive into attention. So first understand that sequence to sequence model is also a neural network architecture. It has got several components like it has got encoder, it has got decoder and a context vector. So context vector I already told you, explained you what it is. Okay. So what is it happening here inside a sequence to sequence model? The encoder is present. First input is given to the encoder. What's your problem? What's your problem? Lagging short with time. I would appreciate your very important, very in that I am teaching you sequence to sequence modeling. Sequence to sequence modeling mein again you have got an encoder and a decoder, both of them. So encoder will take the input sequence and it tries to compress. What it is trying to compress? Compress it into a fixed size context vector. Basically it will consist of again sequential models like RNN, LSTM or GRU only. So when you are preparing the sequence to sequence model, you are again preparing LSTM models only. Okay, but what it is doing, it is trying to convert that input sequence into a context vector. Okay, now after that, what is this context vector? It is a single vector. Try to understand. Context vector is a single vector which comes as an output out of an encoder. It actually summarizes the entire input sequence that has been given. So that one context vector will actually give you the summary of that entire input sequence. That's why this particular thing is mostly used in text summarizations. Okay. So now this particular vector is then passed on to decoder. Decoder I am not diving much into detail because decoder part you will be seeing when you will be building your transformers and everything along with using attention. So I am just giving a brief overview about this encoder and decoder part. So what happens in the decoder is the decoder will take this context vector as an input and it will generate you the output sequence. Again, decoder is also a neural network. It will have its own recurrent layers. It will have its own LSTM GRU models only. Okay, and then it produces one output token at a time until the end of sequence is reached. So that means, say to an encoder, I am telling, hello, I am Priyanka. Okay, and I am doing a machine translation. Then this hello, I am Priyanka will be compressed into one context vector at the encoder end, and decoder will take this context vector, try to generate its token into some other language, let's say Hindi, Namaste, मैं Priyanka हूँ. Are you understanding this? So this entire thing is happening through this encoder and decoder model only. ठीक है ना? So now encoder, decoder, sequence to sequence model is clear. Okay. Now sequence to sequence model has got its own issues. क्या issues हैं? Now it is harder to train. Why? Because the longer will be the sequences, the greater will be the temporal dependency. Temporal dependency means its dependency on time. Time dimension will be more. So more the time dimension, it will require heavy computations. So it is harder to train. Also, if you are using, see I told, encoder, decoder are nothing but recurrent neural network models only. But of course, there will be vanishing gradient descent problems whenever you are using long sentences. You can tell me, madam, if you are using RNN, then it's okay, but if you are using LSTM, how? So I'll tell you, LSTM also can work till a certain extent. Okay, there will be vanishing gradient problem in LSTM also if the corpus is very humongous. Very humongous. But again, one more problem that you are facing with LSTM is everything is sequential in nature. You are going to process one after another in sequence. There is no parallel computation that is happening inside LSTM. So, but of course, it is going to take lot of time and effort to reach towards your output. So, that is also one of the drawback of sequence to sequence model. Plain sequence to sequence model. Now, bottleneck problem, very important. There is this bottleneck problem in this sequence to sequence model. What is it? It refers to an issue where the entire input sequence has to be compressed into a single fixed sized context vector. And this context vector will be then utilized by the decoder to regenerate your output. So that is your bottleneck problem. And as I told you, parallelism again is one of the problem. So all these were few issues that were present with sequence to sequence modeling. Now, the bottleneck issue, as I already told you, it is particularly pronounced with long input sequences wherein the model might struggle to retain and use all relevant information from the beginning to the end. क्योंकि वो sequence by sequence काम करेगा. So for that, what is going to happen? It cannot retain everything from start towards the end sequentially everything. So that's the bottleneck problem. So what is the solution to this particular problem? It is attention mechanism. Attention mechanism, for an example, the moment I have, say for an example, I'll go to this previous slide, okay na? And you people are talking over there. You don't know what am I teaching. I just make any one of you stand and say, what am I teaching? You just go to the slide and you don't know. And if suppose something is in there bold, you just say, oh ma'am, you're talking on vanishing gradient descent, you're talking on bottleneck problem. Yes or no? So what are you doing? You are giving your attention. You are not going through everything sequentially. Are you understanding? So that we humans are capable of, not that machine. You are trying to build your human attention ability inside your machine using attention mechanism. That's the basic stepping stone towards building your transformers. Are you understanding? Attention. Paying attention to what is relevant and what is not to achieve parallelism. Okay. Now, so attention mechanism, let me put it down very, very simple format. See, today's session on attention mechanism is just for your understanding to understand attention. I have chosen very simple way of teaching you attention, not diving much deeper into technicalities in starting. So try to understand first what is attention mechanism in a very simpler manner. So we humans humans do not tend to pay attention sequentially. सही है? So if I see something, I will not start from that corner. You know, it actually goes into the front part or the main part. Okay? So we are humans are actually blessed with that. We are actually blessed with two ways of attention. One is conscious attention, one is unconscious attention. You're just randomly going through and something catches hold of our attention, you just concentrate on that. Yeah, so we humans are blessed with that, not the machine. So humans do not tend to pay attention sequentially. We don't start looking at a picture from a corner, but our focus will actually go to the main feature first. For example, this particular slide, है ना? So if I see that first one, I want to observe. But the second one, अरे why is this blurred? Yes or no? As soon as that picture comes, am I seeing it from the top? No, no. I'm just like, अरे why is this blurred? You know, my attention actually caught hold of something that is in between. So that's what we humans actually work with attention. That's how we work. Correct? So humans pay attention in two ways. That is conscious attention and unconscious attention. We would like our neural network to model the behavior of this conscious attention so that they can pay attention to the important part. So conscious attention, as I told you. And this particular slide, if you are talking, not paying attention, I just raise you and you just go through and see the important part. That is your conscious attention. है ना? So you will just give me some relevant answer which is here and there correct only. Na? So that mechanism we actually want to build with our machine. So we would like our neural network to model the behavior of our conscious attention so that they can pay attention to the important part of the input first. Rather than going sequentially, we want to attain that parallelism in our mechanism and focus on something that is relevant. So we want to build that attention mechanism in our machine, and this is done by attention, more commonly known as an attention mechanism, which is like you are trying to blur out the features which are little less relevant and you are trying to figure out what is more important, paying attention to that. Clear enough with attention mechanism, guys? Yeah. Now, what are the applications? Why do we have to study these attention mechanism today? So, we have already learnt how to build a sequential model now. है ना? Now, we require this attention mechanism because it finds its way into most of today's day-to-day application, which is majorly involving NLP. So, what is it? Image caption generation. Given an image, automatically generate the caption. So, attention has to be needed there. Of course, image-based analysis, action recognition, text summarization, text classification, machine translation, speech recognition, and recommendation system. Recommendation system, bole to, what are you doing in recommendation system? For example, you will be correlating with me. I am fed up with that. I type anything on my Google. Let's say I wanted to buy one salwar kameez, and my next all pages of ad on my Insta or any other place, I will be finding what I have searched for. है ना? So what is that? A recommendation system. Even in Amazon, when you are typing a certain sentence, or in Google you are typing a certain thing that I require something like this, it tries to give you some recommendations. So what is it paying attention to? What is your requirement? Are you understanding? So that's where, you know, attention mechanism comes into picture, and it's important for us to learn it. Okay. Now, attention mechanism is crucial in many modern neural network architectures, especially in the tasks that involve NLP and also computer vision. So two major areas of applications of attention are there. That is the reason. Abhi computer vision aayega, then only you can go for image captioning. Yes or no? If you know NLP, then only you can go for text summarization or recommendation systems. Okay. So its primary function is to allow the model to dynamically focus on different parts of input sequence while processing the output sequence. Major important point it is, you are running through your entire input sequences dynamically and concurrently rather than following it up sequentially. Clear enough? That's the beauty of attention mechanism. Now, key components of an attention mechanism, these are key components. How it is involved in what attention mechanism actually you will go for Q, K, V, everything I will teach you. But now, as of now, I am giving you again a summary of attention mechanism. So try to understand it as a process. As a process, what happens in attention mechanism, try to figure it out. Then we will go for a reverse gear and check what are the different types of attention mechanism, how do they differ. If you understand this attention process, you will understand different types also very easily. Okay, so what is this attention process mein? You have got key components of attention which are very important, called as Q, K, V. Very, very important concept again. Please pay attention. Okay, Q, K, V. Q stands for query, K stands for key, V stands for value. Okay, so query is the word or a token for which we are making the prediction. So the word that you are actually using for prediction is your query. Okay, key represents each word of your input sentence. Each token of your input sequence is your key. Key value pairs you have already done, no? You built a vocabulary with key and a value. So that's the thing. So key represents each word and value represents the embedded information of that word. Means the vector relevant to that particular word. So query is the word that you are actually working on. Key is all the tokens that are present inside your vocabulary, and the next one is a value, which is your relevant embedding associated with your word. Clear enough? Q, K and V concept in attention. Now, let me have a quick analogy. Q, what is the next word in the sentence? For example, you are predicting it. Okay, that's your query. K, each word in the sentence tries to provide an answer for you. That is your key. Value, the actual word representations that provide the relevant information. Okay, quickly see a simple example to understand it better. So what are we doing here in this particular example? The sentence is, the dog barked loudly. So what is the query? For an example, you want to have a current word being predicted as, say, barked. Suppose, so barked will be your query. Okay, and keys will be having every token in that sentence. What is it? The dog barked loudly. They all will have a key. And the value will be the word embeddings of all these words. Clear enough? Concept of Q, K, V. The word that you are working on for your output is your query. All of your words or tokens are your keys. Their associated word embeddings are your values. Q, K, V. Now, the query barked will compare its query vector with the key vectors of all the words. Based on the similarity, attention scores will be computed and the values will be weighted according to those scores to compute the final output. This process is important for attention. So that means what? The ones that are closer to, okay, that will be calculated. You calculate attention score here. This is a completely different mechanism or a different process. Please try to understand here. Okay, so what are you trying to do? You are having a query. For that query, this particular query, say bark, is compared to all the keys. What are the keys? The entire tokens. The dog was, say, the dog, sorry, what did I say? The dog barked loudly. So this barked is taking similarity with the, barked is taking similarity with dog, barked, and loudly. So that similarity, you try to calculate attention score, which one is having more. So obviously, barked the, it will be less. Barked dog, okay, little bit similar. Barked loudly, so verb. Explaining the context of that verb it is. So that will be given the better score. Are you understanding, guys, how things are happening here? So This, based on the similarity, attention scores will be computed and values will be weighted according to these according to those scores to compute your final output. So, abhi values kya, attention weights will be more for whom? Barked loudly, obviously for loudly. Next will be say for dogs, least for the. So, like that similarity. Okay, I don't know how many of you remember, there is always a similarity that you would, correlation is also based on the fundamentals of similarity only. Cosine vector you try to find out. है ना? So based on the same norms, we have got certain formulas how we actually calculate these attention scores. And based on those formula, we actually have different types of attention mechanisms also. Okay, so now again, how it works, very simply put down, the attention mechanism works by calculating the weighted sum. This weighted sum tells the model about importance of features. The process of calculating these weights is crucial. It may vary for different applications. And we explain the attention mechanism here in a very general sense. Again, I am telling, which I am going to explain. Now, working of attention mechanism here is basically divided into two parts. The first part is attention distribution that you have to calculate from the inputs. Calculate the attention distribution from your inputs and then calculate the context vector using this attention distribution. So here I am focusing majorly on attention mechanism in encoder. Yes or no? Encoder mein hoga na, you have to calculate the context vector out of a given sequence. So I am here teaching attention mechanism with respect to encoder first. ठीक है? So what is happening? I am going to calculate attention distribution from the input using certain formulae that we will see how to calculate attention scores, and you will be calculating the context vector using attention distribution. Now, attention distribution is what will give weightage to your inputs. Okay. Now, before calculating this, first you have to encode our inputs using a neural network. Encoded representation of inputs are called as keys. Okay. Encoded representation of neural network are called as keys. Another thing that is used to calculate attention distribution is a query. Query means what? What next it is going to, the current word into action which is used for prediction of your output is your query. So another thing apart from keys that you will use to calculate attention distribution is the query. It is a task related representation that could be a vector or a matrix that is based upon the task. Now, what do? Neural network will try to find the similarity between these two. Okay, so it is going to find out the correlation. It is going to compute for the correlation between the key and the query. How does it do? For which you have to create a function called as a score function, which is nothing but a mathematical.
It explains how keys and queries are related by giving an attention score. Like for our previous example, barked and the poorly correlated. Attention score will be less. Barked dog, good correlation. There will be good amount of attention score. Loudly, again barked is a verb and loudly is describing it, so of course there will be good amount of similarity. So like that, for one query, every other related inputs tokens in that sequence will be correlated,
so that you understand semantically which of them could be related to each other. Okay, so score functions, selection of a good score function is important. The two most common square, I am telling you this in a very broader picture. I have still not dived. See, people just start directly with self-attention, dot product attention. I am not starting. I am first telling what is attention. Try to understand that. Why do we require an attention score? How do we do? Attention score is a mathematical function. Either it can take two operations, I am telling. addition, dot product. Again, based on that, we will have different types of attentions. Okay, so I am beginning from a very different concept. You open any other thing on internet, it directly starts with types of attention mechanism. I am not doing that. So try to first understand what it is doing. So attention score mein, the two most common score function that you use is additive and multiplicative attention. Some of these also incorporate learnable parameters. So, very simple way I am explaining these score functions here. Different types. Additive mein what you are doing? You are trying to add. See, this is normal linear transformation that I am doing so far. है ना? You are adding the key, query, key is multiplied with its weights because I told they are learnable. When it is learnable, they have to be associated with their own parameters, weights and biases. So, same, you know, you are using a suitable activation function. Act there is nothing but an activation function. You are using weights associated with key, weights associated with query and a bias. So, when you are adding them, it is additive. When you are multiplying key and query, but of course, one of them should be transformed. है ना? So, this is multiplicative. Then you have general and then you have location based, which I am not diving right now. I want to teach you first what is this additive and dot product ka in detail so that I explain you about self-attention, what is the need of R for us for learning our next exercise. Okay, so these are some common score functions as I told, additive and multiplicative being in generally more important here. Now attention weights. So once you got your attention scores or energy scores also, some places they call it. Now what you will do, you will try to find out the attention weight. Which input has to be given more priority, which has to be given more weight. So it is done, attention weights will be calculated by using a distribution function. Means again a mathematical function will be applied to your attention score and you will get an attention weight out of it. So what are we doing? We are trying to have a key, we are trying to have query, we are trying to get values, we are trying to correlate key and query and produce attention score by using suitable mathematical function. Using distribution function on these attention scores, you will calculate the attention weights. Okay. Okay. Once after that, what you will do, once you have got attention weights, you will try to calculate the context vector. That is the requirement. So before that, before we actually introduce the context vector, here we require another value here. What is it? Values. Because I told values store the corresponding embedding vector. So if I want to calculate context vector, I should also have my values with me. So this vector called value has one-on-one correspondence with the key. So as I told, it's just like a lookup table. Now context vector will be calculated by using another mathematical function. Here for ease, I am calling it as phi. I am just explaining you the process. I am not still diving depth into attention. First understand the process, how things are getting done. These mathematical functions, what they are, we will see. Okay, so here context vector is calculated as phi of alpha comma v, where phi is a function which returns a single vector called as a context vector, and phi is a mathematical operation. Generally, it is a weighted sum. Okay, weighted sum operation. Normally, you all know what is a weighted sum operation, no? Yeah, a normal linear transformation. Okay. So, our neural network will now make use of this context vector to make prediction. So, this is something, a little block diagram that I tried to figure it out for you. You are using key and a query. You apply it to some sort of mathematical function and then you get the attention scores from there, sometimes called as energy scores also, and apply it to a distribution function to get attention weights. Attention weights and values will be taken together by a linear function. Okay, weighted sum operation is calculated and then you generate a context vector. So this is how simply an attention is used inside an encoder to generate a context vector. Able to relate now what I have been teaching you? Now let us dive into working. In a nutshell, attention computes set of attention weights that determine the importance of different parts of input sequence for generating each output token. These weights are used to create a weighted sum of input feature which forms a dynamic context vector. This I have taught you. Now, summary, I told you calculate attention scores, second compute attention weights, then weighted sum of inputs and then outputs. I am not diving much into detail. This will be covered when we will be teaching you transformers. Means how this context vector will be used and then it will be decoded. So I am just leaving it here. Coming to types of attention mechanism, please all of you, please pay attention. Okay. So first one here is Badenow attention, which we also called as additive attention. I told you attention score is calculated by using either addition or multiplication. So when you are using addition, it is additive attention. So the formula there you can see, it computes attention score by combining encoder hidden state HI and decoder hidden state also by using feed forward network, and the combined vector is then passed through a tan H activation function. So overall operation is using an activation function like tan H and using hidden states, adding them together, you create an attention score. Typically, if you are doing that, it is an additive type of attention mechanism. One type. Different type of mathematical operation, different type of attention mechanism. When you are doing addition, it is additive attention mechanism. Next is multiplicative, which is also called as dot product attention. It was introduced by Long in the year 2015. It calculates attention scores by taking dot product of the encoder hidden states and decoder hidden states. Formula is given onto the screen. Simple dot product formula is present. But then in that, the below formula that I have given you, I am teaching you about variant of dot product attention. It is called scaled. Scaled means it is normalized. Normalization ke liye you have an under root D there. Okay. So scales the dot product by the square root of dimension of queries to prevent excessively large values. Scaled dot product attention is majorly used in all NLP based applications. Okay. Now, this is actually used in transformer techniques also. Okay, scale dot product attention. Single-headed attention. Single head and multi-head is again one category, guys. Please try to understand. यहाँ पर this is very important part of transformer. Okay, so single-head attention. In single-head attention, model will use only one set of QKV. Understanding? Whenever you are using only one set of query, key and value, it is single head attention in order to compute your attention scores. Okay, so this can work for simple tasks. However, it has limitation when there are more complex relationship that has to be captured amongst your input data. Okay, very important now for our next exercise, self-attention. So what is this self-attention? It allows the model to relate different positions of a single sequence to compute its representation. And each token in the sequence will attend to every other token that is present inside the sequence. This is called as self-attention, where it is trying to seek attention score of all the tokens that is present inside that particular sequence. Clear? So till now what we were doing was actually a part of self-attention. So what is the important feature? It gives parallelization. Attention scores with our own context try to figure out with this particular query what is the next possible term that I can go for by skipping the remaining parts. Okay, so this inculcates concurrency or parallelism and it captures long range dependencies as well. Its usage is very important in GPTs and BERTs. Okay, So this self-attention is a part of your GPT transformer that you will build. Self-attention formula is Q dot K transform. Q dot K transform is nothing but your dot product of query and key, and you normalize it with under root D. Okay. So what is D? I already told you, right? D is nothing but here square root of the dimension of your key. Okay, square root of your dimension of key. That's it. Next type is a multi-headed attention, wherein you will allow the model to attend different part of sequence with multiple sets of Q, K and V. If you are using single set, it is self-attention. Okay, single-headed attention, sorry. And if you are using multiple sets of Q, K, V, it is multi-head attention. Extend self-attention by using multiple attention heads. It can independently compute attention and their outputs are concatenated and then linearly transformed. Advantage is it allows the model to focus on different parts of sequence simultaneously. For an example, I tell you, I gave you that slide example. Had it been a simple normal thing, then you have to go by each line, each word sequence by sequence. Because of multi-headed attention, you can figure out at different places some important words. That is multi-head attention example actually. Multi-head attention formula is given. I am not diving much into multi-head attention because you will read this in detail once you will start reading transformers. Okay, for now you understand. You will be having multiple sets of Q, K and V when you are going for multi-head attention. Self-attention process, key idea is each token computes attention scores with every other token that is present inside the sequence. Unlike traditional LSTM, where each word's representation is updated sequentially. So here you have to understand why we are studying attention mechanism apart from what we have done so far from LSTM. Why attention is the need. So LSTM में every value is updated sequentially. Takes lot of effort and time. Whereas this attention mechanism, it is used to, compute attention score with every other token, aggregates the information throughout that entire sentence and give you. So parallel concurrency is getting achieved. Parallel operations are getting achieved here. Computational speed will be more. Example guys. The cat sat on the mat. First tokenized. The cat sat on the mat. So suppose you are tokenized it. Next is you have to embed it. You have to create embedded vectors. Example here I have taken length as 3 and I have chosen some random embedded vectors for this token. Now for these particular token you have to create 3 vectors. Q, K, V. Query, key, value. Now, query represents current word, what to look for. Key represent all the words. Value contains actual information or vector that is present inside it. So, in self-attention, query vector, this process is important. I will take 5 minutes of yours and then we can stop it. Okay. So, in self-attention, for each word, query vector is compared with all the key vectors. Similarity between them is calculated through the dot products between each and every keyword and a query. You try to calculate the attention score. Query is compared to each and every keyword. Similarity is calculated and attention score is calculated. So this will provide us with the data that how much you have to focus with how much attention, which word has to be given more weightage, attention weightage when you are calling this particular query. So in that way, you can actually process onto the next words not in sequence. Are you understanding? You will try to figure out which word has to be given more weightage next rather than going sequentially. So here what it will do, try to find out first attention score between the. Suppose query is the. So the and the attention score will be calculated through Q the dot K the. What particular attention that I am using here? Dot product attention. Okay. The and cat. Like this, all of the attention scores will be calculated, taking Q and T, trying to scale it by doing under root dk, and then getting attention scores, getting the probability out of it by using softmax function, multiplying it with value to get your final context vector. So scaling, as I told you, it is done by dividing it with dimension of key vector to stabilize the gradients. And because you are using a probabilistic approach, you are supposed to use a softmax activation function. Things should not go haywire when a large dimension comes into picture. That is also one of the reasons where you try to scale. Softmax function, once the scores of attention are computed, you apply the softmax function to normalize them, that is put it into the range of 0 to 1, that is your probabilistic range. Finally, you calculate your attention weight and it indicates the degree of importance that you have to give to the words that are present in your input sequence. So once you get to know in a list of say 10 words, which word is more important after this current word, you don't have to reach to it sequentially one after another. You can just find out which word is more significant through a calculation of attention weight, and you will give priority to that word next, rather than parsing through each one of them sequentially. Okay, so what is the output? Output is summation of these attention weight into VI, that is your value vector. So finally what you get is an output single context vector that will end your encoder part here using attention. So what you are doing, you are taking all the list, query, key, value, calculating, let's say dot product attention, self attention onto it, and then creating a context vector which is going to actually, it is calculated through calculating attention scores and attention weights to give you an output as a single context vector compressing the entire input sequence. Clear enough? Okay, that's it. Now I end up with the models actually to attention mechanism, what they use, a vision transformer, your chat GPT, all of these uses attention mechanisms. Okay, so thank you for listening patiently. Next we will go for a hands-on exercise on attention.